Hello everyone, today we're going to talk about the sampling theorem. The prerequisites for this material are calculus, linear algebra, and Fourier series. Sampling is a topic of great importance in signal processing and data analysis. Signals often model continuous objects, and the challenge is how to measure them so that they can be stored and processed in a computer, which basically means that we need a representation that depends only on a finite number of values. A common way to achieve this is by measuring the signal or sampling it at specific locations. And the crucial question is whether we're losing any information by doing this. We're going to start by considering a very simple function or simple signal, just a complex sinusoid, in this case with frequency k over t, that is defined on an interval from 0 to t. And what we're going to do is we're going to cut up the interval from 0 to t at n different locations. In this case, n would be equal to 1, 2, 3, 4 different locations, and we're going to measure the value of the signal there. This is a complex sinusoid, so we'll get a complex number at each point. This is the picture. This is the real part of the complex sinusoids. This is the imaginary part, and we're sampling. This would be, in this case, this would be from 0 to t. T is equal to 1 in this case. We're taking this n samples. For this picture, n is equal to 10. And now the question is, these are 10 numbers. From these 10 numbers, can we distinguish these complex sinusoids from complex sinusoids with other frequencies? Can we say, oh, for sure, this is from a complex sinusoid that has this frequency k over t. It cannot be from another sinusoid with a different frequency. And actually the answer is no. Okay, let's take a look at why. This is what the values are equal to. And again, I want to emphasize here there's a lot of indices, so it's important to know what each of them means. K over t is the frequency of the complex sinusoids, and jt over n is the location of the samples, because we're cutting up this interval of length t into n pieces. Okay, and j goes from 0 to n minus 1. And what happens here is that the samples are equal to this because the t's cancel out. And now complex exponentials are periodic with period 2 pi. Why? Because complex exponential is nothing else but a cosine in its real part and a sine in its imaginary part, and both of these guys are periodic with period 2 pi, so the whole thing is periodic with period 2 pi, because we're assuming here an arbitrary integer p. For any arbitrary integer p, if we add 2 pi pj to the argument of the complex sinusoid, it does not change. So now we can just put the p inside like this, because the n's would cancel. And the thing is that this is the exact expression for the samples you would get from a sinusoid that has frequency k plus pn, okay? Actually, wait, k plus pn, right? So we had the k here that represents the frequency. Now we have k plus pn, so this means that a complex sinusoid with frequency k over t produces exactly the same samples as a complex sinusoid with frequency k plus n over t, k plus 2n over t, and so on. Okay, so all of these frequencies result in exactly the same samples. So now you might say, okay, so we cannot distinguish complex sinusoids with frequencies that differ by n over t, or a multiple of n over t. But how about if we consider frequencies that are kind of next to each other? So where k is equal to 0, 1, 2, up to n minus 1. These guys do not differ by n, okay? So the question could be, can I at least distinguish those complex sinusoids? To explore this question, we're going to define the vectors of samples coming from the complex sinusoids, and we're going to call them discrete complex sinusoids. Okay, so remember, when we sample at these n locations, we end up with this expression for the entries of the sample of the vector of samples. We take n samples, so the vector of samples is going to be in Cn, okay, because it's complex. And we're going to say that the complex sinusoid has frequency k if the samples come from a complex sinusoid with frequency k. Okay, I want to really make a difference between these two different indices. K is the frequency. Okay, so there's n different vectors that we can define depending on whether the original continuous frequency is equal to any of these n values. Okay, and then j, on the other hand, that's the index of the vector. So these are vectors of dimension n. We have n dimensions, n vectors of dimension n, and we want to know if these vectors are linearly independent, because we want to know whether we can distinguish from what original frequency they came from. Okay, again, restricting ourselves to only these n possible continuous frequencies. Okay, in order to see whether they're linearly independent, well, before that, let's take a look at an example. So for n is equal to 10, we would have n different vectors. This is this is the vector corresponding to a frequency of 2. These are the entries. So here, the entries are different values for j, and here the value for k is equal to 2, just to be clear. The frequency is 2, so we see that the original continuous sinusoid had 2 periods within the interval of length t. Okay, this is the interval of length t. If k was equal to 3, here we're changing k to equal 3, then we would have 3 periods within the interval of length t. And again, we're only taking those samples. Okay, those are the samples that go into this vector of dimension 10 in this case. All right, so let's see if these guys are linearly independent. We take the inner product between them. They are complex vectors, so we have to take the complex conjugate of the second one. This is a product of exponentials, so it's an exponential of the sum. And now we have two cases here, depending on whether this is equal to 0, i.e. whether k is equal to L or not. If k is equal to L, then this is equal to 0. We have the exponential of 0, and it's just equal to 1. So the whole sum is equal to n, which means that n is equal to the inner product between psi k and psi k. This just tells us the squared L2 norm of these vectors, which is equal to n. Okay, so the norm of each of them is square root of n. More interestingly, what happens if k is different to L? In that case, we have a geometric series. Okay, this is of exactly this form, where r is equal to x of I to pi k minus L over n. And if you remember your geometric series, this is just equal to 1 minus r n over 1 minus r. Okay, that's what that is equal to. So when we plug that in, and we obtain this expression for the inner product. But now, this on the top, we see that this n cancels out with this n, and we get exponential of I times 2 pi times an integer. And because the complex exponential is periodic with period 2 pi, this is just equal to exponential of 0, which is equal to 1. Okay, so this is 0, and exponential of 0 is equal to 1. It cancels out with this one, so that is equal to 0. So this n vectors of these n-dimensional vectors are orthogonal, which is pretty cool because it means that they give us a basis, an orthogonal basis of Cn. And in particular, it means that we can distinguish between these different frequencies as long as we restrict ourselves to those n frequencies. Okay, so now that we have that in place, we're going to consider some more complicated signals, which are much more useful in practice, because in practice we're not going to be sampling pure complex sinusoids or pure sinusoids. Okay, that's just not going to happen. It's much more practical to, we need to model more complicated signals. And a relatively simple model, but that is super useful in practice to model real data, are bandlimited signals. Bandlimited signals are equal to their Fourier series up to a certain maximum frequency Kc, which we call a cutoff frequency, because that's what people call it in signal processing. That's a maximum frequency. That's the component that oscillates faster in the signal. The frequency of the component that oscillates faster in the signal, it's bounded by a certain value Kc over T, which we call the cutoff frequency of the signal. Okay, again, these are signals, I should have said it, these are signals that are supported on an interval from 0 to T, okay? And they're exactly equal to their Fourier series. So they can be written as a linear combination of complex sinusoids, which are weighted by the Fourier series coefficients, which are complex numbers. Okay, so they're just a linear combination of complex sinusoids, these signals. In particular, because we are limiting the maximum frequency to be Kc, remember that we always also need negative frequencies because we have to be able to represent any possible phase shift in these sinusoidal components. If you don't remember that point, maybe you should go and review the video or the notes on Fourier series. Because we have a maximum value for the frequencies, this means that the band-limited signals with a certain fixed cutoff frequency have a finite representation. They can be completely they are completely determined by their Fourier coefficients, and there's only 2 Kc plus 1 of them. Okay. So the reason why I'm bringing this up is that we're sampling signals, right? We're taking a finite number of values, and we want to represent the signal with just using this finite number of values. If the signal inherently has a finite representation, it depends on a finite number of parameters, then it seems possible that we may be able to recover it from this finite number of samples, as long as we make the assumption that indeed the signal has this form. Okay, and essentially that's the main idea behind the sampling theory. Okay, so now the idea is that we're going to take this class of signals, these band-limited signals, we're going to assume that the signals are band-limited with a maximum frequency that we know. We know that, the maximum frequency is like, 100 over T or something, where T is the length of the interval. We're going to sample such signals at n locations that, again, divide the interval from 0 to T in n equal subintervals. And then we're going to try to recover the signal from those samples. So maybe I'll draw a picture. We have now we have an arbitrary signal. Okay, that's a terrible picture. Let me try to do something else. Wow. I don't know why I'm incapable of drawing a function. Like this, maybe it does like that, then it does like this. Wow, This is... So now you can see why I use lights instead of just writing everything, because I'm incapable of either writing or drawing in a reasonable way. Okay, so how about that? So now again, this is a band-limited signal. It's restricted to an interval of length, an interval between 0 and T. Now we cut it up, because I'm lazy, I'm gonna just cut it up into maybe, we're gonna, do as if these intervals are of equal length. Okay, each interval is of length T over N. And now we sample the signal. This is the value, this is the first value, this is the second value, third value, fourth value, fifth value. Okay, we sample this signal and now we want to recover it. And the idea here is that if the maximum frequency is bounded, so we fix it to be, 10 over T or whatever, then there won't be that much change between intervals, or at least the signal will vary smoothly between intervals because it cannot like change very, very quickly. And that's going to allow us to be able to determine what the values of the original signal are. Okay, that's kind of like the intuition. Perhaps a better intuition is that we're taking a finite number of samples, but the signal depends on a finite number of parameters because it only consists of 2kc plus 1 frequencies. If we manage to estimate those Fourier coefficients, we're done. We can recover the signal, the continuous signal exactly. So we're estimating a finite number of parameters from a finite number of measurements. So that might work out. Okay, that's the intuition. Okay, so now let's take a look at what these samples look like, these samples that I just drew here. Of course, I drew them for a real signal, but this here we're considering an arbitrary complex valued signal that is equal to its Fourier series. So we sample, again, maybe I'll stress that again. Here the frequency of the component is k over t, and we're sampling it at jt over n. And there's this cancellation between the t's, so that we end up with a linear combination of discrete sinusoids. This makes a lot of sense because the original continuous signal is a linear combination of continuous sinusoids. So it just stands to reason that when we sample it, because when you sample a continuous sinusoid, you get a discrete sinusoid. When we sample the band-limited signal, we get a linear combination of discrete complex sinusoids. Okay, so this is just equal to this. And now we ask, under what conditions can we recover these guys, the Fourier coefficients that completely determine the band-limited signal, from this guy? That's the key question here. Okay, we're going to write this system of equations where, remember, that we take n samples, so j is between 0 and n minus 1. Okay, we're going to write this system of equations as a vector xn, which contains the n samples here, okay, equal to this sum. We can write this, if you realize, as a matrix where you have psi 0, no, sorry, you have to start at psi of minus kc to psi of kc. Okay, and here you're going to have x k0 down to sk of, and oh no, sorry, I don't know why I'm starting at 0. It's x of minus kc down to x hat of, oops, sorry, I don't know what I'm doing there. I got confused by my own notation. Minus kc to x hat of kc. Okay, this is exactly, I mean, I'm just representing this sum 1 over t here as a product of a matrix time the vector of Fourier coefficients, and this guy again is just a vector that has x of 0, x of t over n down to x of n minus 1 t over n. Okay, is this vector of coefficients. So now you may, well, a natural question to ask is, when can we recover this this vector of Fourier coefficients from this vector of samples? And essentially we can recover it if, on the one hand, this matrix is tall, so there are more equations than unknowns. That's basically linear algebra. And also this matrix has to be full rank. Okay, so when can we recover, when can we solve this system of equations? Two conditions. On the one hand, you need more equations than unknowns. This guy has dimension n, this has dimension 2kc plus 1, so we need this basic condition where we have more samples than the number of frequencies that we're trying to recover. That makes a lot of sense, the number of Fourier coefficients that we want to recover. And on the other hand, we need to see whether these basis functions that we're combining to produce the signal, whether they're linearly independent. Because if not, you could have two possible sets of Fourier coefficients producing exactly the same samples. Okay, so now let's take a look at where n is equal to kc plus 1. If n is greater than 2kc plus 1, is exactly the same argument holds. If n is smaller, then we're going to have problems, and we'll talk about that later on in the video. But for now, let's assume that n is indeed equal to 2 times the maximum frequency plus 1. When I say maximum frequency, by the way, the maximum frequency is actually kc over t. But you're going to have to forgive me because I make that mistake a lot. I'm just assuming that we have an interval of length 1, which anyways we do in a lot of the examples. Okay, so let's take a look at these guys. This, in particular, I'm going to be interested now in the negative frequencies. Because remember, if I go back, we have already done part of the work. We have actually shown that if you have this n different, maybe let's go back even more. So if we had this family of discrete complex sinusoids where the frequencies went from 0 to n minus 1. And we showed that those n discrete sinusoids, okay, psi of 0 to psi of n minus 1, these guys are orthogonal. So if we had those guys, if those were the guys that were the columns of this matrix, we would be completely fine because they're all orthogonal, so of course that matrix is full rank. I hope you're not getting dizzy by me going back and forth, but my point is that if these guys, instead of going from minus kc to kc, were going from 0 to n, we know that they are orthogonal, so of course that matrix is invertible and we're fine. Okay, so now let's take a look at whether we're fine or not. So it turns out that our problem essentially are these guys, right? Because we know that from 0, so again, I just want to make this super clear. We know that from psi 0 to psi n minus 1, all of these guys are orthogonal. So the positive ones in particular here are orthogonal. But what's up with these guys? Oops. What's up with the negative ones? So we're going to assume again that n is equal to 2kc plus 1, so we have enough samples to estimate the Fourier coefficients. In that case, remember that psi is just equal to x of I 2 pi k, the entries, I mean. Okay, j is not an entry that I want. L over n, okay? This is the entry of psi k of L, the Lth entry of psi k, okay? It's of this form. So in particular, this is periodic with period n, because if I have here instead I have L plus n or some multiple of n, here I will have I of 2 pi k L plus n over n. So this is just going to be equal to I 2 pi k L over n plus I 2 pi k 2 pi k. Okay, and remember, and we'll be using this all over the place, the complex exponential is periodic with period 2 pi. Okay, so if we shift it by 2 pi times a multiple of 2 pi, it does not change, which means that the frequencies here are periodic with period n. And in particular, if we're considering, for example, psi of minus kc, it's exactly equal to, so maybe the j here could be confusing, psi of minus kc is equal to psi of minus kc plus n, but n is equal to 2 kc plus 1. So this discrete sinusoid is just equal to psi of kc plus 1. Okay, psi of minus kc plus 1 is equal to psi of kc plus 2, and so on and so forth. Which means that, okay, this is exactly the same where j, I mean here, I don't know why I put this j here, I think this was a bad choice. So here j is equal to 0 up to j is equal to kc minus 1, okay? This index j that I've decided to. So I decided so that this would show you in generality, but I think it might be more confusing. In any case, what I just showed you is that psi of minus kc, because of this periodicity of the discrete sinusoids in their frequency, is equal to psi of kc plus 1. Psi of minus kc plus 1 is equal to psi of kc plus 2, all the way to psi of minus 1, that is equal to psi of n minus 1. Which means that if we look again at these columns that we have, at all of this, so these are the columns of the matrix that are, here. Sorry. These are the columns of these are the basis functions that we have in this sum. Those are actually equal to, so these are the columns that we have. Okay, sorry. These are the columns that we have from minus kc to kc, because the ones from minus kc to minus 1, and under the condition that n is equal to 2kc plus 1, because those guys, these ones, are equal to the frequencies between kc plus 1 and n minus 1, this means that all the frequencies in that sum can actually be mapped, if we reorder them, to psi from 0 to n minus 1. So this was a bit painful, but it just means that because of the periodicity of these discrete sinusoids, those vectors in that sum are all orthogonal. Okay, they're all orthogonal, and this is the key. Because of that, we're going to be able to recover the Fourier coefficients from the samples. Because as long as n is equal to 2kc plus 1 or greater, these vectors are all orthogonal. Okay, so how do we recover? Well, because these vectors are orthogonal, we can just recover by taking inner products with them. Okay, so if we're interested in the kth Fourier coefficient, we take an inner product with psi k. And now, because the samples from the band-limited signal can be written like that, we have this inner product here. We can take out the Fourier coefficients, and now we have the inner product between discrete sinusoids that are between 0 and n minus 1, okay, because we have done this mapping due to the periodicity. And all of these products are going to be 0, except if m is equal to k. If m is equal to k, that is equal to 1, because we're normalizing by 1 over square root of n. So we get the Fourier series coefficient back, which means that we can completely reconstruct the band-limited signal. And that's the celebrated sampling theorem. The celebrated sampling theorem tells us that we have a band-limited signal that is a linear combination of continuous complex sinusoids that has a certain cutoff frequency kc over t, because it's, again, the signal is restricted to an interval of 0 to t. It can be exactly recovered from n uniformly spaced samples, so just n numbers, as long as n is greater than 2 times the cutoff frequency plus 1. Again, the cutoff frequency is really kc over t, okay, but 2 kc plus 1. That's known as the Nyquist rate in the literature. And the way you can recover is by just taking inner products between the samples and n discrete sinusoids, because those n discrete sinusoids are orthogonal. And the underlying key here is that because the signal is a linear combination of complex sinusoids, when we take the samples are linear combinations of discrete sinusoids, and if we restrict ourselves to only consider frequencies between minus kc and kc, then those discrete sinusoids are all orthogonal, so we can extract any component that we want by taking inner products with those sinuses. Of course, this requires that we know in advance what is the cutoff frequency of the band-limited signal. Okay, so this is used in practice all over the place, and in particular it's critical in audio. So it turns out that the range of frequencies that human beings can hear is between 20 Hertz and 20 kilohertz. Me, I'm already older than most of you guys, so probably I can't hear things at 20 kilohertz. So then you could think, okay, at what frequency should we sample? So just to be clear, hertz here means that we are considering intervals of 1 second. Okay, these are frequencies that correspond to an interval of 1 second. So in that case, t here would be equal to 1 second. So what should be the number of samples? It should be just double that plus 1. The plus 1 here doesn't really matter because these numbers are so large. So we should be above 40. We should take more than 40 samples per second. And in particular, these are typical rates that are used to sample audio. People tend to take for 44,000 samples per second, 48,000, 88,000, 96,000. Okay. This is what was used for CDs. Of course, this makes me look really old that I'm including that here. Some of you, I wonder if you know what a CD is. Okay, so now we're going to do a very simple example to just drive home the main points that we have explained. We're going to consider a real sinusoid with frequency equal to 4 Hertz. So that means that t is equal to 1 over s. So k, like the maximum frequency kc, is 4 and minus 4. Okay, like remember, so this is minus 4 and this is 4. So remember that we need negative frequencies because we have to account for phase shifts, and that's, you know, part of why all of this becomes very complicated, but you know, that's just life. Okay, so now what is the cutoff frequency and what's the number of required samples? I just told you the cutoff frequency, so, but anyways. So think about this, maybe stop the video for a moment just to make sure that you understand the basic ideas. Okay, so the cutoff frequency is just 4 because we have only 2 frequencies, minus 4 and 4. The maximum value is 4. The number of required samples has to be 2 times kc plus 1, which is equal to 9. Okay, so here, yeah, we're right, 4 Hertz, 9, perfect. So we're taking this more than 9 samples. Let's take a look at an example where we take n samples from this signal. Okay, so we're taking we're dividing the interval of length 1 into 10 subintervals and taking one sample at the beginning of each interval at 0, 0.1, up to 0.9. Okay, so the band-limited signal is a linear combination of complex sinusoids. So in particular, the samples are linear combinations of samples from complex sinusoids, which are just discrete sinusoids. Okay, these are discrete sinusoids where n is equal to 10 and k is equal to minus 4 and 4. Okay, so that's what the samples, the discrete samples, the vector of 10 samples is equal to. 0.5 times the discrete sinusoid with frequency minus 4 plus 0.5 times the discrete sinusoid with frequency 4. Okay, so now, you know, n is equal to 10, so from psi minus 4 to psi 4, they're all orthogonal, as we had proved, because these guys are essentially, if we reorder them, the same as psi of 0 to psi of 9. Okay, if you reorder them, actually psi of 8, but it doesn't matter. Okay, so just because there's just 9 of them. Okay, so to recover, we take inner products with the corresponding discrete sinusoids. And we're going to do this for the entries that we're interested in, which are between minus 4 and 4, because we're assuming a cutoff frequency of 4. Remember, the samples have this form. When we take an inner product with psi minus 4, these guys are orthogonal. Again, we have shown that. So we're going to end up with the inner product between this and this. And that's just going to be 0.5 because we're dividing by 1 over n, okay? And remember that when we divide this guy by 1 over square root of n and this guy by 1 over square root of n, those are orthonormal vectors. Same thing happens here. Now, this guy and this guy, the inner product is 1. This guy and this guy, the inner product is 0. We again get 0.5, which is the true value of the Fourier coefficients. And what happens for all of the rest? Okay, where k is not equal to 4 or minus 4, those guys are orthogonal. So we're just going to get 0. So now we reconstruct our signal. First, we take a look at what Fourier coefficients we have recovered. They're all 0 except for minus 4 and 4. And now we build the recovered signal by combining those continuous sinusoids, and boom, we have recovered the signal exactly. Okay, like here in blue we have the signal, in red we have the reconstruction, perfect reconstruction, we're very happy, the sampling theorem has worked for us. Cool, so now let's see what happens, because I have told you that a key point here is that you need to know what your cutoff frequency is and you need to sample accordingly. But what if here, you know, we are misinformed and we think that the maximum frequency is 2, even though it's really 4? So what happens? Well, there we're going to say, okay, so how many samples do we need? We need 2kc plus 1 sample, so 5 samples are going to be enough. Okay. However, we have a problem, which is that discrete sinusoids, you know, the discrete sinusoids are periodic in their frequencies with a period of n. So in this case, you know, if you change the frequency by 5, the discrete sinusoids remain the same. Okay. Here, by the way, I have a small typo where this should be 1/5 up to 4/5. Okay, because that's where we're sampling. We're sampling at 0, 1/5 up to 4/5. Okay. So this is going to come to haunt me because it's going to appear at every slide, but whatever. Okay, we're sampling from 0. So we're sampling the 5 samples in the interval from 0 to 1. Okay, so now what happens? We know that these samples are equal to 0.5 psi minus 4 plus 0.5 psi 4, but now n is equal to 5. So because the discrete sinusoids are periodic in their frequencies with period 5, this guy is equal to what? And now I want you to maybe stop the video and think about it. Psi of what? And of what? That is, so basically here we're expecting frequencies between -2, so -2, -1, 0, 1, and 2. Those are the frequencies that we're expecting because we're misinformed. Does any of these frequencies map to psi of -4 if we realize that these guys are periodic with period 5? Think about it for a moment. The answer is yes. This is just equal to psi of 1. And this guy is just equal to psi of -1, which are within the frequencies that we expect. Okay, so again, you might think, oh, you know, Carlos, he's so lazy. Why is he doing this? Well, the reason is that I've taken like a lot of takes of this video before. So I'm going to ask you to live with that small typo. Anyways, the point here is that the samples that we are taking are equal to a linear combination, of course, of these discrete sinusoids with the right frequencies, but they're also equal to this linear combination of discrete sinusoids with different frequencies, and they're within the range that we expect. So when we reconstruct the signal, we're going to reconstruct these guys instead of these guys. Okay, and that's the key here. And I'm going to show you an example in a moment which shows you that actually this can easily arise in practice, and it's a big deal. Okay, so again, we assume mistakenly that the cutoff frequency is 2. We try to recover by taking inner products with the frequencies that we expect, and we expect -2, -1, 0, 1, and 2. And the thing is that the samples actually look as if they come from 1 and -1. So what's going to happen? Here we're going to get 0 because this guy is orthogonal to these two guys, but there, for -1, we're going to detect 0.5, and the same is going to happen at 1. So now we mistakenly think that the Fourier coefficients at -1 and 1 are actually equal to 0.5, and we're not even, this is not even on our radar, because we think that the coefficients are restricted to be between -2 and 2. So when we recover the signal and we reconstruct it with the wrong frequencies. We reconstruct it with frequencies of -1 and 1, and what happens? We have cosine of 2 pi t. This is what we think the signal is equal to, but it's actually equal to cosine of 8 pi t. And this is called aliasing, because this guy is basically impersonating this other guy. Okay, so the samples look as if they could come from, like these are the samples, they're completely, like they could come from either of these two guys. The truth in this case was the blue, the high frequency signal, but we thought that there couldn't be high frequency sinusoids in our signal, so we screwed up and we reconstructed the red signal. Of course, we have an excuse, which is that it's completely consistent with the measurements. The problem here is that we didn't know that there could be higher frequencies. If we had known, what would we have done? We would have taken more samples. Okay, we'd have sampled at these other places, and then we wouldn't have gotten it wrong, because then the red signal wouldn't have been consistent with the samples anymore if we had taken more samples. And that's the key insight of the sampling theorem. Okay, so aliasing happens when, this is aliasing in general, we have a signal that has cutoff frequency k through over t. This would be 4 in our example. We measure it at 10 samples, but we assume that it is bandlimited with a different cutoff frequency that is smaller. In our case, 2. Okay, and then we're going to pay for that mistake. How are we going to pay for that mistake? If the true cutoff frequency is larger than the cutoff frequency at which we're sampling, because this is the problem, we sample at just twice this smaller frequency. The way we're going to pay is that when we reconstruct, what happens is that we have this inner product again, and we have relied on the fact that these guys were all orthogonal, but that's no longer true if n is equal to 2k samp plus 1, where k samp is smaller than the true frequency, because we're going to have values of m that are equal to k mod n, which means that they're going to produce the same discrete sinusoid, so that inner product is going to be 1. Okay, so we're going to see the Fourier coefficients as sum of the Fourier coefficients for k of all the original signals that are equal to k mod n. Okay, so just to remind you, this just means m minus k mod n equals to 0, just means that m is equal to k plus pn for some integer p. So if there are any of those in the true signal, then they're going to show up in our reconstructed coefficients. This is exactly what happened in our example. In our example, k true was 4, but we thought that the maximum frequency was 2, so we just sampled at 5. So what happened here? What happened here is that when we were reconstructing 1, m equals 4, when we're reconstructing minus 1, m equals 4 appeared, because 4 is equal to minus 1 plus 5, where 5 is equal to n. Okay, so this is consistent. This is just a general statement of our example. The point is that if you don't sample finely enough, you're going to have that the true frequencies can be aliased into other frequencies because of the fact that n is smaller. Let me show you an example in practice. Here we see this electrocardiogram. In practice, the cutoff frequency, you could consider a cutoff frequency of around here, like somewhere above 50, because this is really small. I mean, look at the magnitudes. The magnitudes are almost negligible. You're not going to care about that. That's not even going to show up when you reconstruct. The error is going to be really, really small. So your cutoff frequency should be probably around 50, a bit above 50, right? Because you do see that here you have a pretty large component at 50 and minus 50 due to the power line interference that we talked about in the Fourier series video. Okay, so the signal is approximately bandlimited at 50. In this case, we have 8 seconds of signal. So Kc is equal to 50 times t, around 400. Okay, so to avoid aliasing, we better take more than 800 samples from our signal. Okay, that's what we should do. Okay, here we're taking 1000 samples and we're recovering the Fourier coefficients, and everything works well. You recover. We only assume that there are frequencies between here and here. That corresponds to an n of 1000. and we just ignore the rest because they're so small, and we're quite fine. Okay, we have some small mistakes. These small mistakes are due to the fact that these guys, we're ignoring them, and they're, you know, being mapped inside by aliasing. But we don't care because they're very small. And here you see the signal and the reconstruction and the samples that we're taking. So realize that we're sampling quite finely, and we get a very good reconstruction. Okay, but now what happens if we mistakenly assume that the signal is approximately bandlimited at around 40 Hertz, which by the way is quite reasonable, right? Because you could think, oh, you know, hard signals, why would there be something at 50 Hertz? There's no reason why there would be something at 50 Hertz. Let me sample it as if it was band limited at 40. So I'm ignoring the fact that we have this power line interference here because I don't expect it. So it's not that crazy that you would do that. And if you do that, then what happens? We assume that it's band limited at 40 Hertz, so we take just 600 samples. Okay, Kc is equal to 312 because you have to multiply by the length of the interval. And now, when we recover, we're recovering for each Fourier coefficient, we're going to recover any other Fourier coefficient that exists in the original signal, and is equal to k mod 625. So 50 Hertz, which corresponds to the Fourier coefficient equal to 400, is going to show up where? In the low frequencies, because here we're assuming that the signal only has low frequencies. It's going to show for an m such that m is equal to, for a k, like in which k is this going to show up? It's going to show up for a k that is equal to 400 minus 625 to minus 125. It's also going to show up, because we have a minus 400, it's also going to show up at minus 400 plus n, which is 125. Okay, so, oops, I don't know how to sum and subtract. Clearly, maybe I should go back to high school. Okay, so there you go. I don't know how to do math. Okay, so yeah, the important thing here is that because we have ignored the fact that you could have higher frequency components, we have sampled too slow, and because we sample too slowly, boom, we get this ghost components that appear at 30 Hertz. So, and these are this thing. This is very important because you might look at the electrocardiogram and say, oh, there's something wrong with this guy, like it has these weird fluctuations in the heart signal, maybe like they're severely ill. But what's happened is that this is just this other frequency that is impersonating that because you're not sampling fast enough. In the time domain, okay, what's happened is that we're not sampling fast enough to account for the higher frequency. Again, we have a signal that is perfectly consistent with the samples. The problem is that we're not taking enough samples. Okay, we think that the signal is fluctuating slower than it is. Okay, so this is an issue of enormous importance in practice. You have to be very careful to sample at the right speed and not take too few samples if there might be higher frequency components. In practice, what you would do here, by the way, is to filter out the high frequencies with an analog filter, just electrically, before you sample, to make sure that you don't get aliasing, but those are more technical details. Okay, so what have we learned here? We have defined an orthogonal basis of discrete complex sinusoids, which allows us to represent the samples coming from band-limited signals as a linear combination of orthogonal functions, as long as you take enough samples. And this allows us to recover band-limited signals from a finite number of samples. However, insufficient sampling can lead to aliasing. Thank you very much.